Hello everyone, this is Sarvesh, lecturer in Civil Engineering, Government Polytechnic, Station 1. The course is Reinforced Concrete Structures, and in lecture 4 we are going to discuss design of T-beams, and this lecture is a continuation to the previous lecture. So on completion of this lecture, you are able to know how to determine the moment of resistance of the T-beams and what are the different types of problems involved in design and analysis of the T-beams. And we will solve some example problems in analysis and design of T-beams for different cases for better understanding. Right. And before going to discuss the problems, just I would like to recap whatever we were discussed in last class. In last class, we were discussed the procedure how to determine the moment of resistance of the T-beams and what are the different provisions for transverse reinforcement in T-beams, and we will solve some example problems on determination of effective width of the flange. That means in T-beams, uh, the effective width of the flange you need to determine. So all how to determine for isolated T-beams and other T-beams we were discussed in last class, and also we were solved some example problems for better understanding. Then we have discussed the procedure for solving the problems on analysis of T-beams. That means how to determine the moment of resistance of the T-beam based upon the given data. That means in T-beams, the moment of resistance is mainly depends upon the depth of neutral axis, right? So, because in this case, there are two types. That means if the depth of the neutral axis is within the flange, the determination of moment of resistance is similar to that of the singly reinforced rectangular beam. Okay, right? And if the depth of neutral axis is within the web, then there are two cases will rise, right? So one is if the uh, df, that means thickness of flange by effective depth is less than or equal to zero point 0.2. That means the uh, stress distribution within the thickness of flange is uniform or constant, right? So in that case, you need to determine the moment of resistance by separating the compressive force taken by the flange separate and compressive force taken by the web. So based upon that, you can calculate the moment of resistance. And another case is if the moment depth of neutral axis is within the web and df by d is greater than 0.2, that means the stress distribution along the thickness of flange is not uniform or not constant. That means it is a combination of parabola and rectangle. So in this case, as per IS 456-2000, it is suggested to remold or determine the thickness of flange as per IS 456-2000. That means you need to modify the thickness of flange so that within the modified thickness of flange, the stress distribution is constant, right? So it is proposed separate equation to determine the modified thickness of flange. And in last class, we were solved one example problem on analysis of T-beam. That means the determination of moment of resistance of the T-beam based upon the given data. and there we got the depth of neutral axis is within the web, and it is df by d is less than 0.2. That means the stress between the thickness of flange is uniform or constant, right? And today we are going to solve some more problems, different problems for analysis of TP. So this is another example problem. Uh, Calculate the maximum uniformly distributed load at limit state that the T-beam can carry, including its self-weight on a simply supported beam of uh, span of 5 meters. And the T-beam dimensions are shown in figure. So from here, this is the sorry, this is the width of the flange, that is BF, P of F, and this is the thickness of flange, that means the thickness of slab, that is D of F, and this is the effective depth of the flange, that is 500 mm, and width of the T-beam is web, width of the web BW equal to 250 mm, and this is the area of tension reinforcement, right? So based on these dimensions, just write down the given data. So that is, this is the width of the flange 1500 mm, thickness of flange 100 mm, effective depth is 400 mm, width of web is 250, and area of steel is given as 804 square. And use FCK is 20 Newton per mm square and F of Y is 415 per mm square. Right. So the first whatever we discussed in last class in procedure. So before starting, we don't know where the depth of neutral axis, whether it is in within the plant or within the web, right? And it is not possible to determine it, right? So what we have to do is first we need to assume certain condition. That means if we, you can assume that the width of the depth of the neutral axis is within the flange or depth of neutral axis is within the web. So first we need to assume it, right? So here I am assuming that the depth of neutral axis is within the flange, right? If depth of neutral axis is within the flange, then to determine the depth of neutral axis, equate compression force equal to tension force. C is equal to C, right? So where the compression force is 0.36 FCK BF into XU, and the tension force is 0.87 F of Y into F ST. So from this equation, if you simplify for determining the XU value, you will get 0.87 F of Y into A of ST by 0.36 of CK into A of S, right? So if you substitute the values, that is 0.87 into 415 into 804 by 0.36 into 20 into 1500 equal to 26.88, and compare this XU with respect to depth of flange, right? So because we are assuming that the depth of neutral axis is within the flange. That means whatever you are getting XU, that should be less than or equal to thickness of flange. So what is the thickness of flange here given? The thickness of flange is 100 mm, but we got it is 26.88 mm. So therefore, our assumption is correct. That means the whatever the depth of neutral axis we got, that is less than the thickness of flange. So our assumption is correct. So if our assumption is correct, whatever we have calculated, the depth of neutral axis is correct. So therefore, the XU is 26.88, right? So next step is you need to determine the maximum depth of neutral axis, right? So the maximum depth of neutral axis can be determined by as per IS 456 2000 based upon the grade of T, right? So as per code, it is given that the XC max by D for different uh, grade of T. So here our grade of steel is Fe415 steel. So for Fe415 steel, the corresponding value is 0.48. That is the effective depth of the steel. So here the effective depth is 500, and if you substitute it, so the XU max we got it as 240 mm, right? Then compare these two values, that is XU value as well as XU max value, to classify the type of the build, whether it is a balancer section or under reinforced section or over reinforced section, right? So as we discussed, the limit state method is acceptable for uh, uh, balancer section as well as under reinforced section. So over reinforced sections are over reinforced sections to be avoided as per IS codal provisions. So that is why before going to determine the moment of resistance, it is very important to calculate the both the neutral axis and compare it XU and XU max. So here XU is 26.88 and XU max is 240 mm. Therefore, XU is less than XU max, right? So if XU is less than XU max, then the type of the beam is under reinforced section, right? So for under reinforced section, therefore it is okay. Then go for further steps, that is determination of moment of resistance. Right. For under reinforced section, the moment of resistance is 0.36 FCK V of X V of BF into XU into D minus 0.42 XU. So if you substitute the values, you will get 0.36 into 20 into 1500 into 26.88 into 500 minus 0.42 into 26.88. So from this equation, you will get moment of resistance of the given section is 141.88 into, this is 10 power 6, right? This is not 10 power 6 Newton mm. And if you express in terms of kilonewton mm, this will become as 141.88 kilonewton meters. So this is the moment of resistance of the given T, right? And this is one type of the problem in table. That means the depth of neutral axis is within the flange. So if it is within the flange, so you need to determine the moment of resistance in this process, right? So next one is next we will discuss another type of problem. So for clear understanding, right? So next problem is calculate the safe load. Sorry. So next example 2 is an RCC singly reinforced, simply supported EB has a flange of 750 mm width and 120 mm thickness. Is having area of steel 3500 mm square. Provide at an effective depth of provided at an effective depth of 450 mm. and width of the web is 50 mm. Calculate the moment of resistance of the section using M20 grade concrete and Fe 415 steel. So this is the problem. So in this, first write down the given data. The given data is the width of the flange is 750 mm and thickness of flange is 120 mm, and having a steel area of A of S is 2500 mm square, and the effective depth is 450 mm and width of the web is 250 mm. Right? So just list out whatever the given data is here. So these are the data. That is the P of F, width of the flange is 750 mm, thickness of flange is 120 mm, effective depth of the beam is 450 and BW is 250, and area of steel is 3500 square, and FCK is 20 Newton per mm square, and FFI is 415 Newton per mm square. So here also you can do in the same process. So this is the dimensions of the uh, given member. Sorry, this is how much? Yeah, this is 750, not 700. This is 750. This is 120 and 450. Right. So this is the flange and this is the web. So right. So same as here also we don't know where the depth of the flag is present. Right. So for this case, you need to assume one case whether the depth of neutral axis is within the flange or the depth of neutral axis is within the well. Here I am assuming that the depth of neutral axis is within the flange, right? So therefore, if the depth of neutral axis is within the flange, so for determination of depth of neutral axis, you need to equate compression force equal to tension force. So the compression force here is 0.36 FCK V of F into X2 is equal to the tension force is 0.87 F of Y into V of ST. And here XU equal to 0.87 F of Y into A of ST by 0.36 FCK into B. Right. So from this equation, if you substitute the values, that is 0.87 into 415 into 3500 by 0.36 into 20 into 750, you are getting 234 mm. This is the depth of neutral axis as per our assumption, right? Then compare this depth of neutral axis with respect to the thickness of flange, right? To determine whether our assumption is right or wrong. So here the thickness of flange is how much? 120 mm, and the depth of neutral axis calculated is 234 mm. Therefore, here the depth of neutral axis is greater than the thickness of flange. That means the neutral axis is not within the flange, right? It is within the web. That means whatever we assume, so whatever we are assumed, that we assume that the neutral axis is within the flange, that is wrong, right? So our assumption is wrong. So therefore, the depth of neutral axis is within the web. If the depth of neutral axis is within the web, then the determination of depth of neutral axis procedure is different. So use that equation and determine the depth of neutral axis again, right? So, so this is the equation for depth of neutral axis, right? So here the compression force is divided into two parts. That means the compressive force taken by the um, what is this web and the compression force taken by the flange, right? And another important thing is if the depth of flange, if the depth of neutral axis is within the flange, there are two cases will rise. One is if the df by d, that means the thickness of flange to effective depth of the beam is less than or equal to zero point 0.2 or greater than zero point 0.2. If df by d is less than or equal to zero point 0.2, that means it represents that the stress distribution, the compressive stress distribution within the thickness of flange is constant, right? And if it is df by d is greater than zero point 0.2, then the compressive stress distribution within the thickness of flange is not uniform. That means it is a combination of rectangle and parabola, right? So here, first you need to check whether it is greater than zero point 0.2 or less than or equal to 0.2. So in our case, the df by d value is 0.26. That means it is greater than 0.2. That means uh, what you call the stress distribution along the thickness of flange is not uniform. It is a combination of rectangle and parabola, right? So in this case, it is very difficult to determine the compressive stress because the stress distribution is not uniform. Suppose this is the thickness of flange. Let us say, so if this is a stress distribution diagram, so this is the this is so this is so that means up to here it is rectangular portion, then it is started the parabola, right? So what happens in this case, it is very difficult to estimate the compressive force directly. So in this case, as per IS 456 2000 proposed to modify the thickness of flange to make that the stress within the thickness of flange is uniform. If it is the thickness of flange, within the thickness of flange, if the compressive stress is uniform, then it is easy to determine the compressive force taken by the flange, right? So in our case, the df by d is greater than 0.2. Therefore, the stress is not uniform within the thickness of flange. Therefore, you need to determine the modified thickness of flange as per IS 456 2000, right? So as per IS 456 2000, the modified thickness of flange is YF, that is 0.15 XU plus 0.65 D of F, where XU is the actual depth of the neutral axis and D of F is the thickness of flange. And remember, this value should not be sorry, should not be greater than the D of F, that is thickness of flange, right? So if you substitute the values here, XU is also unknown. Remember, we have to determine the XU value. So how to determine XU values? The XU value should be determined by equating the compressive force equal to tension force, right? So in first case, we assume that the neutral axis is within the flange and corresponding equation we have used to determine the XU. But what happens if we compare where XU is greater than DF? That means it is our assumption is wrong. Then come to the second case, then the depth of neutral axis is within the wave. Then there are two cases rises, whether it is greater than 0.2 or less than or equal to 0.2. So in our case, it is if you know this one, then only you can use the appropriate formula to determine the depth of neutral axis, right? If you don't know in which case it will come, then it's very difficult to use the formulas. So here it is greater than 0.2. Therefore, you need to determine the depth of neutral axis corresponding to the modified thickness of flange, that is y of f, right? Here, the y of f is also in terms of xc, right? If you know the xc value, then only you are able to determine the yf value, right? So therefore, xc is unknown, so keep it like that. Then substitute d of f, so overall value you will get it as 0.15 xu plus 78. So this is effect as equation 1, right? Because I don't know the x value, right? So therefore, after modifying this one, then that means I am assuming that the stress within the thickness of flange is uniform, right? That means if I draw the stress distribution diagram for the same case, and this is called as I can say this is the modified thickness. For example, this is called as y of f, right? So within this, let us say our neutral axis is somewhere else here. So within this, it is assuming as rectangle, then it is going to be like parabola. So up to here it is constant. This is 0.45 fck, right? So therefore, the compressive force here we can divide it into two parts: the compressive force taken by the flange and the compressive force taken by the web. I can divide like, right? So here the compressive force, suppose this is the neutral axis, and I can take it right. So compressive force taken by the flange, how much? The BW, that is width of the web, P of F minus PW, we will get this portion distance and this portion distance. So that means average stress into area, right? Average stress is here and here it is same, therefore this is 0.45 FCK into area is nothing but this length into this thickness, that is y of f. So this length, so because this portion is already included in the web portion, you just deduct this one, that is P of f minus BW into y of f. That is the compressive force taken by the flanges, and compressive force taken by the web is XU, average stress is, so for this portion the average stress is 0.36 FCK, area is BW into X, and tension force is same 0.87 F of Y, right? So same concept we have used here and determine the depth of neutral axis. So the compressive force is compressive force taken by the web and compression force taken by the flange. 0.36 FCK into BW plus 0.45 into F of CK into V of F minus BW into Y of F equal to 0.87 F of Y into Y of ST. So here Y of F is also unknown. So substitute this equation, whatever we have determined here for Y of 4 to determine Y of F, this value, right? Substitute same value here to determine the X. Therefore, here, right? So if you substitute this value, so the total equation is within the everything is known except X, right? Then substitute the values, that is 0.87415 into 3500 minus 0.45 into 20 into 700 minus 250 into Y of F is this value, that is 0.15 XU plus 78. So substitute that one and equal to 0.36. So this is by, right? Because this total by is not equal. This one is not equal by 0.36 20 into BW, that is 250. if we solve this equation, because everything is known except x, right? If you substitute y of that equation into here, then everything is known except x cube. So from this equation, you can determine the value of x, that is 368 mm, right? So after getting this x value, again you need to check, calculate the y of f and check whether it is greater than thickness of flange or less than thickness of flange. So as per the codal provision, the thickness of flange, y of f should be less than or equal to the thickness of flange, right? So substitute this xu value in this equation and find out the y of f, right? If it is greater than d of f, then you need to redo the calculation, right? First check whether your value is less than thickness of flange or greater than thickness of flange. So for that, yeah, here x is 368, 368, and before going to extreme max, just find out the y of f, that is 0.15 xu plus, yeah, before going to calculate the y of f, again it is very important point is you need to check whether your xu is equal to xu max, less than xu max or greater than xu max. This is very important because see, as per the IS 456-2000 codal provisions, the limit state method will not accept the over reinforced section, because see, if over reinforced section, the word itself says over reinforced, that means you are providing the more reinforcement in tension zone. Therefore the failure will occur in compression zone. The compression zone is only concrete, right? So concrete will fail suddenly, cannot give any, the deformation of the concrete is very less, so therefore it will fail suddenly. So as per codal provision, the IS 456-2000 will not allow the sudden failures. So for that purpose, we are avoiding the design of over reinforced section. So it is very important, before going to next step, you need to check whether your section is under reinforced section, balanced section, or over reinforced section. So for that, you need to determine the XU value, XU max value, that is maximum depth of neutral axis. So this maximum depth of neutral axis can be determined as per IS 456-2000 based on grade of steel. So for grade of scale 415, the XU max is 0.48 D, where D is the effective depth of the beam. So if you substitute the values, that is 0.48 into 450, you will get 260 mm, right? Then you need to compare with your actual depth of neutral axis versus maximum depth of neutral axis. Why we need to compare? To classify the section or to classify the type of failure, whether it is balanced section or under reinforced section or over reinforced section, right? So if you compare it, then our XU is 368 mm and XU max is 216 mm. That means the XU is greater than XU max, right? That means whatever the depth of actual depth of neutral axis is much more greater than the maximum depth of neutral axis. So that means it is an over reinforced section. So we need to avoid the over reinforced section design as per codal provision. So how to avoid? So for avoiding the over reinforced sections, I would like to restrict my depth of neutral axis to maximum depth of neutral axis. That means it will become as balanced section, right? That means if I restrict my depth of neutral axis to the maximum depth of neutral axis, then the condition for x equal to x max is nothing but your balanced section. So therefore, restrict your xu equal to xu max. Now what is the depth of neutral axis here? 216, right? So like this you need to check before going to the further steps. It is very important because see here it is clear, if it is greater than this, if you use same value, that means you are allowing the overlying forces section. So it leads to the sudden failure of the structural members because of high steel intention, right? So that is very important. So after checking this, so here we got xu is greater than xu max. Therefore, the overlying forces section. So therefore, I am restricting my actual depth of neutral axis to xu max. So therefore, now the xu becomes 216. So for corresponding to this xu, then what is the modified thickness of flange? That is y of f. So y of f is equal to 0.15 xu plus 78 is equal to, if you substitute the values, 0.15 into 260 plus 78 get 110.4 mm. So this is the modified thickness of flange, right? That means within this thickness of flange, the stress is constant, right? Then you can go for further steps. Yeah. Then calculate the moment of resistance of the section. So now if you know, if we are modifying thickness is calculated, right, and it is less than the thickness of flange, then now it is similar to the depth of neutral axis within the web, and d of f by t is less than 0.2. The only difference is df will become as y of f, right? Only that is the difference, and same, the concept is same. So first we can calculate the moment corresponding to the moment developed or moment of resistance for the flanges. That means just we like to draw the diagram for clear understanding. Right now, this is similar. For example, right. So here, so I can divide into this part. Now the moment of the resistance taken by the flange of thickness y of f, right? So how to calculate this is the stress, the load, compressive load on this member. That means area of average stress into area. So average stress is 0.45 FCK into area is this is BW, right? So this is B of F. B of F minus BW into Y of F. That is the total compressive force taken by the flanges into lever arm is, so from here to center of this one, that means D minus Y of F by 2. So that is this one. So 0.45 FCK into B of F into BW into Y of F, which is the compressive force taken by the flanges into lever arm, that is D minus Y of F by 2. Similarly, for this case, this up to this one. So for a web, the moment resisted by the web is the average stress into area of the web into lever arm. So in this case, average stress is nothing but 0.36 FCK into XT max, right? 0.36 FCK into Xc max into BW is the area, and this is the average stress. Then depth of neutral axis is D minus 0.42 Xc max. Right? If we substitute the values, that is 0.36 to 20 into 250 into 216 into 450 minus 0.42 into 216 plus 0.45 into 20 into 750 minus 250 into 110.4 into 450 minus 0.5 into 110.4. This will be as 335.82 into 10 power 6 Newton mm. And this will become as 335.82 kilonewton meters. Right? So this is how you have to determine the moment of resistance of the T-beam. That means, see, with the depth of neutral axis within the web, then you need to check for two criteria, right? When df by d is greater than 0.2 or less than or equal to 0.2. If it is greater than or equal to greater than 0.2, then you need to calculate. So what we have done, you need to calculate the modified thickness of flange. Then you need to check corresponding formula should be used to determine the XU. And after determining, you need to compare to the X max, and corresponding that you have to determine the moment of resistance. Right? This is how you need to determine the moment of resistance of the T-beam. Right? So so for this, I would like to conclude the today class. So just summarize what we were discussed today. Today we have solved two different type of example problems for analysis of T-beams and how to determine the moment of resistance and the safe load that the beam can carry based upon the given data. Right. For that we have solved one example problem in first case, that means based upon the given data. So first we have assumed the depth of neutral axis, because in starting we don't know where the depth of neutral axis, whether it is planned or whether it is where. So if you know, if you are assuming the depth of neutral axis and corresponding the equation, you can use it. So we have determined the depth of neutral axis, and we have checked with thickness of flange. So we got it as the depth of neutral axis is less than the depth of flange. That means our assumption is right. So therefore, then we have calculated the Xt max and compared with the depth of neutral axis, and we checked that our beam is under the exposed section. So accordingly, we have used the formula and determine the moment of resistance of the T-beam. Similarly, for the second problem, based upon the given data, we have calculated the moment of resistance, and same method also we have used here. That means we are assumed that the depth of neutral axis is within the flange, and corresponding formula used to determine the depth of neutral axis. But what happens in second case, the depth of neutral axis is greater than the depth of flange. That means our assumption is wrong, right? So that another thing is the df by d value is greater than 0.2. That means the stress is not uniform within the thickness of flange. So that means this is the case 2. Again in case 2, second case, B case. That means you need to uh, remove, uh, you need to determine the modified thickness of flange to make that the stress distribution is uniform within the thickness of flange. As per coded provision, is given a different method to determine the modified thickness. That equation also within the depends on the XC value, that means depth of metal axis, right? So use that is called as YF. Use that equation and find out the equation in terms of XU, and corresponding equation should be used to determine the depth of neutral axis, right? So corresponding equation, just substitute y of f in terms of xu. So everything is known except xu, and find out the xu value. And again, you need to calculate the xu max and check whether your xu is equal to xu max or less than xu max or greater than xu max. So in our case, we got it as xu is greater than xu max. That means over reinforced section. The limit state method, in limit state method, we should avoid the over reinforced section. So therefore, I have to restrict my depth of metal axis to maximum depth of metal axis, that is xu equal to xu max. So corresponding to xu max, then calculate the modified thickness of flange, and then determine the moment of resistance for corresponding to this modified thickness. So this is how you need to solve the problems. Uh, so, so therefore, in the next class we will solve some more different types of problems, right? For this, I would like to conclude it. So, thank you.